Welcome to IT Support Training, where we begin our exploration of the fundamental responsibilities and technical knowledge required of modern help desk specialists. In this introductory chapter, we will outline the professional landscape of IT support and set the stage for your technical journey. This course is an unofficial, independently produced guide. It is not affiliated with, endorsed by, or connected to CompTIA or any other certification body in any way. All trademarks belong to their respective owners. This content is for informational and educational purposes only. Choosing to master IT support is a commitment to understanding how enterprise environments function under the hood. This course provides a comprehensive roadmap that bridges the gap between basic hardware troubleshooting and complex network administration roles. We focus on the practical skills that distinguish a competent technician from a novice, ensuring you understand the core mechanics of modern computing. By investing your time here, you gain the structured knowledge necessary to navigate the complexities of corporate infrastructure efficiently. I have designed this material to be rigorous and grounded in industry standards, giving you a competitive edge in your career. We will start by examining the hardware that powers our systems, moving through motherboard architectures, storage technologies, and power management. From there, we transition into the foundational networking models, including the OSI stack and IP addressing, which are essential for any network practitioner. You will learn to navigate various operating systems, manage user permissions, and perform critical administrative tasks via both graphical and command line interfaces. We also place significant emphasis on the systematic troubleshooting methodologies that prevent recurring failures in a professional environment. Finally, we discuss how to wrap these technical skills in professional customer service and proper documentation habits. The help desk structure is traditionally divided into 3 tiers, each requiring a different level of technical depth and autonomy. Level 1 support serves as the first point of contact, where technicians handle password resets, basic software reinstalls, and connectivity checks. When these issues require more advanced intervention, they are escalated to Level 2, where technicians often handle complex configuration issues and server-side troubleshooting. Level 3 represents the engineering tier, where specialized software architects or developers resolve systemic flaws and deep-rooted platform stability issues. Understanding this hierarchy allows you to recognize where your specific role sits within the organization and how to communicate effectively with escalations teams. Beyond the technical hardware and software configurations, a successful career in IT relies heavily on the integration of soft skills and professional conduct. Even the most robust technical solution is incomplete without proper documentation recorded in the ticketing system, which maintains historical data for future reference. We will look at the professional life cycle of a ticket, from initial intake and categorization to resolution and closure. You will also learn how to establish a virtual laboratory environment, allowing you to practice risky configurations without impacting live enterprise systems. This hands-on approach is the most effective way to internalize the abstract concepts we discuss throughout the course. As we prepare to dive into these topics, keep in mind that this syllabus is aligned with industry-recognized paths such as CompTIA A+, and Network+. These certifications validate your knowledge, but are merely benchmarks. The true value lies in your ability to apply these concepts to unique, real-world scenarios. We will explore the progression from general help desk support into specialized pathways like cybersecurity or advanced systems administration. Your career trajectory is not a static line, but a series of decisions based on the technical domains you find most compelling and manageable. We're going to build a solid foundation so that you can navigate this professional growth with confidence and technical accuracy. I look forward to our next session together. Hello, and welcome to our deep dive into the physical foundations of computing, starting with motherboard components and CPU architecture. We're going to deconstruct how these complex systems actually communicate at a hardware level. The motherboard is the nervous system of any computer, dictating how components interact and what scale of performance we can expect from a build. We start by distinguishing between common form factors like ATX, micro ATX, and IDX, which define the physical dimensions and mounting points for the board within a case. While ATX boards offer extensive expansion slots and high-end power delivery, micro ATX and IDX alternatives prioritize space efficiency, often at the cost of reduced PCIe connectivity. Understanding these standards is critical because they dictate the compatibility of the overall system build and the eventual ergonomics of the workstation. Alongside these form factors, we have to look closely at the CPU socket itself, where we encounter two primary technologies, namely LAN grid array and pin grid array. In an LGA socket, the pins reside on the motherboard, whereas a PGA setup places the pins on the processor itself, necessitating care during installation to avoid bent pins. By mastering these physical interfaces, you remove the guesswork from building or maintaining workstations that require specific component pairings. To facilitate communication between the processor, memory, and peripheral devices, motherboards utilize a chipset architecture typically split into two functional roles. Historically, the North Bridge managed high-speed traffic between the CPU, memory, and the graphics processor, while the South Bridge handled slower input and output operations like USB, SATA, and networking. Modern architectures have largely integrated most of these functions directly into the CPU, but the legacy of the chipset as a controller for system flow persists. We look at this through the lens of bus speeds and PCIe lane distribution, which dictate how much bandwidth is available for expansion cards like high-end GPUs or high-speed NVMe storage drives. If a user complains about slow throughput on a secondary drive, it might not be a failing component, but rather a configuration where PCIe lanes are shared or throttled by the chipset. Understanding these traffic patterns is an essential skill for any IT professional diagnosing bottlenecks in workstation performance. Firmware serves as the critical intermediary between hardware startup and the operating system, shifting from the traditional BIOS to the more robust UEFI interface. The Unified Extensible Firmware Interface allows for larger boot drives, faster startup times, and improved security, most notably through features like Secure Boot. Secure Boot ensures that only trusted, digitally signed code can execute during the startup process, serving as a primary defense against rootkits and boot-level malware. Beyond security, your ability to navigate the UEFI menu allows you to manage system health and overclocking parameters, which brings us to the thermodynamics of computing. Overclocking the CPU or RAM pushes them beyond their rated specifications for performance gains, but this inherently increases power consumption and heat generation. Managing this requires a solid understanding of cooling systems, including passive heat sinks, active fans, and liquid cooling loops that circulate fluid to transport thermal energy away from sensitive silicon. Stability at the hardware level relies heavily on power delivery through sophisticated voltage regulator modules located on the motherboard. These modules take 12V direct current from the power supply unit and step it down to the lower voltages required by processors, smoothing out fluctuations to ensure a steady supply of power, even under load. When a system fails to start or crashes during intensive tasks, the root cause is often linked to an unstable power supply or an overloaded VRM phase failing to regulate current correctly. We must also cultivate an eye for systematic troubleshooting by interpreting the post-error codes that a motherboard emits when a boot sequence fails. These codes, represented via audible beeps or diagnostic LED arrays, map to specific failures in hardware initialization, such as memory detection issues or graphics initialization errors. By recognizing these symptoms of hardware fatigue, you spend less time guessing and more time providing accurate, effective support to the end user. I will see you in the next lecture. Welcome back. This chapter focuses on the essential components of memory and storage architecture that dictate system performance and data persistence in modern computing environments. To understand computer storage, we must first distinguish between volatile and non-volatile memory components. Volatile memory, such as your system RAM, requires a constant power supply to maintain the information stored within its cells. When you shut down your computer, data in volatile memory is cleared, which is why it serves as a high-speed workspace for the CPU rather than a long-term filing cabinet. In contrast, non-volatile memory or storage retains its contents even when the power is removed, making it the bedrock for our operating systems and files. Hard disk drives and solid-state drives are the most common examples of non-volatile storage, acting as the primary repository for your software applications. Understanding this boundary is critical because it forces us to consider how we manage data flow between these two states to ensure both high performance and data integrity. If we treat storage like memory, we suffer from slow throughput, and if we treat memory like storage, we face data loss when a power cycle occurs. Mastering these fundamentals allows you to diagnose why a system might be hanging or why data is not persisting as expected after a reboot. Moving into the realm of random access memory, we have seen a significant progression from DDR3 to the current DDR5 standard. Each generation increases the data rate and power efficiency, but they are physically keyed differently to prevent accidental installation in incompatible motherboards. Within the workspace, you will frequently encounter SATA modules, which are essentially shrunken versions of standard DMM modules designed specifically for the limited physical space inside laptops. For enterprise environments, we often specify ECC, or error correction code memory, which is designed to detect and fix data corruption on the fly. Non-ECC memory lacks this parity checking, which makes it faster and cheaper, but susceptible to bit flips that could cause a system crash in high uptime scenarios. Furthermore, we must consider channel configurations, where placing memory sticks in matching pairs or quads allows the memory controller to access multiple modules simultaneously. This increases the total bandwidth available to the processor, effectively reducing the bottleneck commonly associated with memory-intensive workloads. Storage hardware has evolved dramatically, pivoting from the mechanical constraints of spinning HDD platters to the instantaneous access provided by NAND flash SSDs. A mechanical drive uses magnetic heads that must physically move to a specific location on a rotating disk to retrieve data, introducing latency measured in milliseconds. Conversely, SSDs utilize flash memory cells that provide electrical access to data, bringing latency down to the microsecond level, which transforms the entire user experience. Within this space, the interface matters immensely, as we see a shift from the legacy SATA interface to the more advanced NVMe protocol. SATA is limited in its throughput by the AHCI command set originally designed for spinning media, while NVMe is specifically architected for non-volatile storage on the PCIe bus. This allows for massive parallelism and significantly higher data transfer speeds, which is why the M.2 form factor has become the industry standard for modern, high-performance computing. To manage data reliability and speed, we frequently rely on RAID, or redundant array of independent disks, to manage multiple physical drives as a logical unit. RAID 0 provides exceptional performance by striping data across multiple drives, but offers no redundancy. If one drive fails, you lose everything. To combat this, RAID 1 mirrors data across two drives, ensuring that if one fails, an exact copy remains available for continued operation. For larger storage pools, RAID 5 uses parity to distribute error-checking information across at least 3 drives, providing a balance between speed and fault tolerance. In high-performance server environments, RAID 10 combines the benefits of mirroring and striping to deliver both massive speed and high levels of protection against drive failure. Regardless of the configuration, you should always monitor drive health using SMART data, which provides predictive alerts by tracking internal drive metrics like reallocated sectors and spin-up time. While internal storage is the core of the machine, we frequently interact with optical drives, tape drives for long-term archiving, and external connectivity standards. Optical media like Blu-rays are less common today, but still find use in specific data distribution scenarios, while tape drives remain the gold standard for off-site disaster recovery due to their longevity and capacity. For external devices, USB-C and Thunderbolt have consolidated the chaotic landscape of previous connectors into a single, high-bandwidth universal standard. Thunderbolt, in particular, carries enough throughput to connect external graphics cards or RAID arrays without feeling like you are using an external peripheral. This connectivity flexibility allows us to extend the utility of our base systems, but it also introduces new failure points that you need to troubleshoot during your help desk duties. Always verify that both the cable and the port support the required protocols to avoid performance, throttling, or connection instability. I will see you in the next lecture. Welcome back. In this chapter, we explore the critical domain of power delivery and thermal management, which serves as the physical foundation for every reliable computer system. Selecting a power supply unit requires a precise calculation of your total system wattage, accounting for the combined power draw of the CPU, GPU, storage drives, and cooling fans. It is common practice to calculate your total estimated power load, and then select a unit that offers at least a 20% buffer beyond that requirement to ensure the supply operates efficiently without constantly hitting its maximum capacity. Efficiency is quantified through 80+ ratings, which measure power conversion efficiency under various load levels, ranging from standard 80+ up to titanium. A higher efficiency rating indicates less energy is dissipated as heat, which leads to lower operational costs and a more stable environment for your hardware components. When dealing with international deployments, you must check if a power supply features an automatic voltage switch or a manual toggle for 115V versus 230V operation, as incorrect settings can lead to catastrophic hardware damage. Always remember that the power supply is the heart of the system, and skimping on its quality is a decision that often precedes hardware failure or data corruption. Physically connecting the power supply involves several standardized cables that provide specific voltage rails to different components. You will primarily interact with the 24-pin ATX connector, which serves as the primary power source for the motherboard and low-power onboard peripherals. For the CPU, you will find 4-pin or 8-pin EPS connectors that provide dedicated, stable power specifically to the processor power phases. Graphics cards move significantly high current, necessitating the use of 6-pin or 8-pin PCIe power cables, which are distinct from the CPU EPS cables and should never be interchanged. If you are ever in doubt, the labeling on the connectors or the unique plastic tab shapes serve as physical safeguards against improper insertion into hardware slots. Always ensure these cables are fully seated and that the locking plastic clip on each connector has engaged to prevent loose contacts that can cause signal interruption or electrical arcing under high load. Maintaining a healthy internal climate within a computer chassis relies on the deliberate management of airflow dynamics. A well-designed system typically implements a high-pressure or balanced airflow configuration where intake fans at the front pull cool air in and exhaust fans at the rear and top push heat out. You want to avoid turbulence and stagnant heat pockets, which often form around storage bays or behind thick bundles of cables that impede the front-to-back path of air. Regularly monitoring system temperatures via software utilities serves as your primary diagnostic tool to identify potential thermal throttling, which occurs when a CPU or GPU automatically reduces its clock speed to prevent permanent heat damage. If you observe temperatures exceeding defined thresholds under basic workloads, it is generally an indicator that your cooling solution has failed or that the case ventilation is physically obstructed. Troubleshooting power supplies requires a structured approach because these units are often the first suspect when a computer exhibits erratic behavior. Symptoms of failing supply include spontaneous reboots during high-load tasks, system freezes, or in severe cases, the audible sound of electricity, a strange smell, or smoke. Never attempt to open or repair the internal components of a power supply, as the capacitors can store a lethal electrical charge long after the unit has been disconnected from the wall outlet. Beyond internal failure, you must protect your hardware using surge protectors to mitigate common electrical spikes and uninterruptible power supplies, or UPS units, to guard against complete power loss. A UPS provides critical battery backup time, giving the operating system enough duration to perform a graceful shutdown, thus preserving the integrity of your file system and preventing data corruption. Handling sensitive electronic components requires a strict adherence to electrostatic discharge, or ESD, prevention protocols to avoid invisible damage to integrated circuits. ESD can induce microscopic failures within the silicon of a CPU or memory stick, defects that may not manifest immediately but significantly reduce the expected lifespan of the hardware. The gold standard for a grounded workspace involves using an anti-static mat and a proprietary wrist strap that connects you directly to the chassis ground or a dedicated earth point. If a professional anti-static station is unavailable, you should at least minimize the buildup of static by frequently touching the unpainted metal surface of the computer case before handling any internal hardware. By building these small, repetitive safety habits into your workflow, you ensure that you're not the primary cause of the hardware failures you are tasked to diagnose and repair. I will see you in the next lecture. Welcome to another session where we look at the physical connections that bridge the gap between human intent and computer execution. Today we address the complex ecosystem of peripheral devices and the standards that govern their interoperability. Connectivity starts with understanding the evolution of data transmission standards. Historically, serial and parallel ports provided the foundation, but today we operate in a landscape dominated by universal serial bus iterations. USB 3.2, for instance, marks a significant shift in data throughput, utilizing multi-lane operation to achieve speeds that render older standards obsolete. When we discuss USB-C, we are looking at a reversible, high-bandwidth connector capable of handling power delivery, data transfer, and video signaling simultaneously. This versatility addresses the mechanical failures of older, pin-based connectors, though it introduces complexity regarding protocol support under the same physical pinout. Being able to distinguish between a USB-C cable that only carries power and one that supports DisplayPort alt mode is a fundamental competency for any modern helpdesk technician. Beyond general-purpose data buses, display interfaces have transitioned through several critical iterations to support higher resolutions and refresh rates. VGA remains a legacy analog standard, functioning by transmitting intermittent red, green, and blue voltage signals, which are highly susceptible to electromagnetic interference over long cable runs. In contrast, HDMI and DisplayPort operate in the digital domain, utilizing transition minimized differential signaling or packetized data to ensure signal integrity. DisplayPort is particularly favored in professional multi-monitor setups because of its ability to daisy-chain monitors through a single port via multi-stream transport. These digital signals essentially treat the monitor as a network node, allowing for precise synchronization that analog standards simply could not achieve. When configuring these displays, maintaining the correct resolution requires an understanding of the handshake process, where the extended display identification data, or EDD, is communicated from the monitor back to the source hardware. The seamless integration of these peripherals relies heavily on the marriage of hardware and the operating system. Plug-and-play, or PNP, was designed to abstract the configuration process away from the user, relying on the operating system to query a device for its vendor ID and product ID. Once the hardware notifies the system of its presence, the operating system attempts to match these identifiers to a device driver, which is essentially a specialized slice of code that acts as a translator between generic kernel calls and specific hardware registers. Should a driver fail to load correctly, the device manager becomes our primary diagnostic interface. By examining status codes and hardware IDs in this utility, we can often determine if a failure is rooted in a missing resource, a corrupted binary, or a resource conflict that requires manual intervention. While modern Windows environments are remarkably adept at automated resolution, an IT professional must understand how to manually roll back or update these files when automated processes reach their logical limit. Specialized peripherals often move beyond standard local connections, entering the realm of networking via power over Ethernet, or PoE. This standard, defined under the IEEE 802.3 group, allows network infrastructure to supply electrical power to devices like VoIP phones or IP cameras over the same twisted pair wiring used for data. This is achieved by injecting a DC voltage onto the data lines, requiring that both the switch and the power device adhere to the same power handshake protocol to prevent damage to legacy NCs. Because this power must travel over copper cabling, cable quality and length become critical constraints. Excessive resistance in substandard cabling results in voltage drops that can lead to intermittent reboots or complete device failure. Understanding the difference between active PoE, which performs a signature detection, and passive PoE, which is always on, is vital to ensuring the health of the infrastructure you are managing. Input devices and signal conversion are the final pieces of the puzzle when building a reliable workstation. Keyboards, mice, and biometric readers are straightforward, but KVM switches represent a more sophisticated implementation of shared resource management. These allow multiple computer systems to be controlled by a single set of peripherals, which necessitates careful management of emulated signals to ensure the operating systems don't lose track of the mouse or keyboard when the focus switches. In environments involving audio, MIDI connectivity remains a distinct standard, functioning as a digital communication language for instruments rather than audio itself. When converting between analog signals and digital processing, we must be mindful of the noise floor and the limitations imposed by cable shielding. Proper grounding and high-quality shielded cabling are not merely technical preferences, but requirements to minimize signal degradation, especially in professional environments where electromagnetic noise from nearby power lines or networking equipment could otherwise introduce audible or data-level interference. I hope this clarifies the necessary standards for your practical work. See you next time. Welcome to our exploration of mobile and laptop architecture. In this session, we will break down the intricacies of portable hardware and the management strategies required for enterprise compliance. Laptops represent a fundamental shift in hardware design compared to the modular nature of desktop systems. Because space is at a premium, heat dissipation is managed through slim, specialized cooling fans that often pull air from underneath the chassis and exhaust it through vents near the screen hinge. You should be familiar with the placement of Wi-Fi antenna wires, which usually run along the perimeter of the LCD bezel to maximize signal reception despite the metallic casing found in most modern Ultrabooks. Integrated webcams operate over a USB internal bus protocol, and replacing them typically requires a complete disassembly of the display housing, which can be fragile due to the use of strong adhesive strips instead of screws. When you're tasked with upgrading or replacing a laptop keyboard, you must identify how the manufacturer secures it to the top case, as some are integrated into the palm rest and require migrating all internal components to a new chassis. Screen replacements involve careful management of the display cable connector, which is notorious for being delicate and prone to failure if not seated perfectly flat before applying power. Mobile operating systems such as iOS and Android manage hardware resources entirely differently than their desktop counterparts, largely by enforcing strict sandboxing for applications. This software isolation ensures that one application cannot easily access the memory space or data of another, which creates a stable but restricted environment for the end user. When hardware issues arise, such as a localized failure in touchscreen responsiveness, you first need to determine if the issue is a digitizer problem or a software calibration error. Battery swelling is another critical condition where chemical degradation causes gas buildup inside the cells, and you must never attempt to puncture or force a swollen battery back into the enclosure, as this poses a severe fire risk. Proper disposal protocols for lithium-ion batteries are mandatory in any professional IT environment to ensure both safety and environmental compliance. You will often encounter power management settings in Windows that conflict with modern standby modes, requiring you to understand how AC adapter wattage must meet or exceed the laptop's power draw requirements to prevent the system from throttling its CPU performance under load. Mobile Device Management, or MDM, serves as the primary mechanism for enforcing security policies on heterogeneous hardware fleets within a corporate ecosystem. By enrolling a device in an MDM platform, administrators gain the ability to push global configuration profiles, manage application installations, and remotely wipe sensitive data if a device is reported missing. This process relies on certificate-based authentication to verify that the mobile device is trusted by the corporate network before it is granted access to internal mail servers or file stores. Wireless synchronization and data migration represent the logical side of this management, where protocols like Microsoft Exchange, ActiveSync, or proprietary cloud-based services ensure that user profiles remain consistent across multiple physical devices. Managing cellular data roaming configurations is also vital for field personnel, as incorrect settings can result in significant financial liability for the organization if the device connects to unauthorized towers while traveling abroad. You must understand how to configure access point names and roaming limits to keep costs predictable while maintaining essential mobile connectivity for remote employees. Short-range wireless communication standards allow for a seamless user experience, but require precise configuration to avoid potential security holes. Bluetooth pairing relies on the secure, simple pairing process, where devices exchange public keys to establish an encrypted link, and you should ensure that discovery modes are turned off once the pairing is established to prevent unauthorized scanning. Near-field communication, or NFC, functions primarily at high frequencies over extremely short distances, making it ideal for authentication tokens, but insufficient for bulk data transfer. When troubleshooting connectivity, always check the physical antenna state before diving into driver configurations, as accidental damage to the Wi-Fi card often results in intermittent packet loss that mimics software corruption. Maintaining a consistent approach to hardware documentation ensures that when you see a specific laptop model, you are already aware of the internal component limitations and the correct path for disassembly. These internal component configurations are the foundation of providing reliable support in a mobile-heavy workspace, where downtime is synonymous with productivity loss. I will see you in our next session. Welcome back. Today we are diving into the mechanisms and maintenance of various printer technologies. Printers remain a persistent source of friction in any IT environment, often because they occupy a space between mechanical engineering and software configuration. To support them effectively, you must understand the underlying physics of how an image is transferred onto a physical substrate. Impact printers, such as dot matrix models, use mechanical pins to strike an inked ribbon against paper, which is a process still utilized in specific environments requiring multi-part forms. Inkjet printers operate on a completely different principle, relying on tiny nozzles that spray liquid ink droplets directly onto the medium by heating the ink or using piezoelectric vibrations. While these are common in smaller offices, they differ significantly from the complex process of laser printing. Laser printers function by utilizing electrostatic charges, light-sensitive drums, and thermoplastic toner powder. Thermal printers, often used in receipt printing or labeling, rely on heat-sensitive paper or thermal transfer ribbons to create images, making them highly efficient for specific industrial use cases. The laser printing process is a sequential series of events that you should be able to visualize when troubleshooting print quality issues. It begins with the processing stage, where the print data is converted into a bitmap image by the printer's formatter board. Next, The charging step uses a primary corona wire or roller to apply a uniform negative charge to the rotating photosensitive drum. During the exposing phase, a laser beam strikes the drum, neutralizing the negative charge in specific areas to create a latent electrostatic image. In the developing stage, toner particles, which are also negatively charged, adhere only to the areas of the drum where the laser reduced the static charge. The paper is then charged and passes under the drum to perform the transferring step, pulling the toner onto the surface of the paper. Finally, the fusing assembly applies intense heat and pressure to melt the toner into the paper fibers, while the cleaning blade removes any leftover toner from the drum to prepare it for the next print cycle. Maintenance often involves identifying when a specific component has reached the end of its useful lifespan and requires a physical replacement. Fuser kits are common where items that include a heating element and pressure rollers. When they fail, you will likely encounter repeated paper jams or toner that smears because it did not properly bind to the paper. Transfer belts are another critical component in color laser printers, serving to carry the sheet of paper across the 4 toner cartridges. If this belt shows physical damage or wear, you will see inconsistent color registration or streaks. Pickup rollers are small, rubberized components that feed paper into the printer from the tray. Over time, these rollers lose their grip due to paper dust buildup or wear, leading to frequent missed feeds or paper jams. Proactive maintenance schedules, typically dictated by high-volume usage counters, are the best way to prevent total printer downtime in an enterprise setting. Beyond hardware, connectivity and software management often present their own unique set of challenges in a network environment. Setting up a network printer generally involves assigning a static IP address to the device or using a print server to manage incoming traffic from multiple workstations. When a user experiences a print failure, you must investigate the print queue or check if the local spooler service on the machine has crashed or hung. Driver compatibility remains a frequent point of failure, particularly when transitioning between different versions of Windows or Mac OS where legacy drivers may not function correctly. If you encounter ghosting, where a faint copy of a previous image appears on the page, the issue is almost certainly within the drum unit or the cleanup mechanism. Fading, conversely, is usually a symptom of a low supply of toner, although it can also indicate a failing high-voltage power supply. While office printing is standard, you might also be tasked with supporting 3D printing technologies in modern collaborative spaces. Understanding 3D printing begins with the concept of additive manufacturing, where material is deposited layer by layer based on a digital 3D model. Fused deposition modeling is the most common method, which utilizes a filament, often PLA or ABS plastic, that is melted and extruded through a heated nozzle onto a build plate. You should treat the nozzle and the build plate as critical components that require level calibration and periodic cleaning to prevent clogs. Managing these devices shares some similarities with traditional printing in that you must manage print temperature, feed rates, and firmware settings. Keeping the build environment stable and ensuring the material is protected from moisture is essential for producing reliable, high-quality output in these systems. I will see you in the next lecture. Welcome back. In this lecture, we will examine the open systems interconnection model to understand how data moves across complex network infrastructures. When we discuss networking, we are essentially talking about how different hardware and software components communicate despite being manufactured by various entities. The OSI model serves as the foundational conceptual framework for this communication, abstracting the complexity of data transmission into 7 distinct sequential layers. By breaking down the process into these layers, we gain a common language for troubleshooting and design that remains relevant even decades after its inception. The physical layer, or Layer 1, deals with the raw electrical, mechanical, and procedural interface of the transmission medium, such as cables and bitstream signals. Moving up to Layer 2, the data link layer, we encounter the world of MAC addresses and frames, which dictate how data is transmitted between nodes on the same local segment. Layer 3, the network layer, is primarily concerned with logical addressing via IP and the routing of packets across disparate networks. As we ascend to the transport layer at Layer 4, we define the reliability of the conversation through mechanisms like TCP, which ensures delivery, or UDP, which prioritizes speed over guaranteed arrival. Higher layers in this stack focus less on the hardware and more on the structure and presentation of data for the user. Layer 5, the session layer, initiates and manages connections between applications, ensuring those conversations remain separate and synchronized. The presentation layer, or Layer 6, acting as a translator, handles character encoding, encryption, and data compression, ensuring that the receiver can understand what the sender has formatted. The application layer at Layer 7 is the interface with which the human user or the software services interact. A critical aspect of this model is the mechanism of encapsulation, where at each level, additional header information is wrapped around the data as it descends from the application down to the physical wire. When the data reaches its destination, the reciprocal process of de-encapsulation occurs as each layer strips its specific header and passes the payload upward. Understanding this constant wrapping and unwrapping is the key to identifying where a failure occurs in a communication path. To translate this theory into practical technical support, we must map specific network hardware to these layers, which helps us isolate failures systematically. A network switch is the primary device acting at Layer 2, as it makes forwarding decisions based on hardware MAC addresses. Conversely, a router functions at Layer 3 because it interprets IP addresses to determine the best path to a destination network beyond the local segment. When a user reports that they cannot access a website, a structured technician starts from the bottom of the OSI model. We verify the physical connection first, then check link status at the data link layer, and only then proceed to verify network routing and service availability. This approach prevents the common pitfall of wasting hours chasing configuration issues when the root cause is simply a disconnected Ethernet cable. It is worthwhile to briefly compare this 7-layer structure with the TCP or IP stack that is actually implemented in most modern internet environments. The TCP IP model typically collapses the session, presentation, and application layers into a single application layer and combines the physical and data link layers into a network access layer. While the TCP IP model is more descriptive of what engineers actually build today, the OSI model remains the gold standard for education and diagnostic methodologies. By thinking in terms of the 7 layers, we avoid the ambiguity of lumped-together functions and can pinpoint exactly whether a problem is one of voltage, a logical address conflict, or a protocol handshake failure. Mastering this model allows you to transition from blindly plugging in cables to understanding the actual flow of digital information within the enterprise. I will see you in the next lecture. Welcome back. And today we turn our attention to the fundamental structure of Internet protocol addressing, which is the cornerstone of all network communication. Understanding how devices are identified and how they route traffic is an essential skill for any IT professional. An IPv4 address is a 32-bit logical address, typically represented in dotted decimal notation, consisting of 4 octets separated by periods. Each octet represents 8 bits, meaning each segment can hold a value from 0 to 255, providing a total of over 4 billion potential combinations. In the early days of networking, address space was managed through a classful system, where classes A, B, and C determined the division between network and host portions based on the leading bits of the address. However, this method proved inefficient and wasteful, leading to the adoption of classless interdomain routing, or CDR. This modern approach uses a variable length subnet mask to define the network boundary, represented by a slash followed by the number of bits allocated to the network prefix. For example, The /24 notation indicates that the first three octets constitute the network ID, while the final octet identifies the individual host. Because the pool of available IPv4 addresses is finite, we rely on RFC 1918 to define private address spaces that are not routable on the public internet. These ranges, such as 10.0.0.0.0/8, 172.16.0.0/12, and 192.168.0.0/16, allow internal networks to function independently of global address exhaustion. To enable these private devices to interact with the broader internet, we use Network Address Translation, or NAT, which maps private local addresses to a single public IP address at the edge of the network. While NAT effectively extends the life of IPv4, it is fundamentally a workaround necessitated by the depletion of public addresses. This exhaustion prompted the development of IPv6, which increases the address space exponentially by using 128-bit addresses represented in hexadecimal. IPv6 addresses are expressed as 8 groups of 4 hexadecimal digits, though we often apply shortening rules to collapse strings of zeros using double colons to keep configurations manageable and readable. Beyond the addressing scheme itself, a host needs specific parameters to participate in a local area network or reach external systems. The subnet mask defines the scope of a local network, allowing the machine to determine if a destination IP is reachable directly or if traffic must be sent to the default gateway. The gateway serves as the exit point for the network, usually the local router, acting as the intermediary to send packets to remote or external networks. If a device is configured for dynamic IP allocation, it requests these parameters from a DHCP server during the initial connection handshake. Conversely, static IP allocation involves manually entering these details, which is preferred for servers or networking hardware that require persistent identity. If a client fails to reach a DHCP server, it will often invoke APIPA, assigning itself an address in the 169.254.0.0/16 range as a clear diagnostic flag that the host is unable to receive network configuration parameters. Subnetting is effectively an act of dividing a larger network into smaller, broadcast domain-isolated segments to optimize traffic flow and reinforce security. By calculating the appropriate subnet mask, administrators can group related devices, reducing the overhead of broadcast traffic that would otherwise traverse the entire network. This segmentation also allows for the application of different access control policies between subnets, ensuring that sensitive data remains isolated from less secure zones, even if they are physically co-located. Furthermore, we frequently use the 127.0.0.1 loopback address to verify the integrity of the local network stack, as sending a request to this address tests the loopback interface without sending data over the physical wire. Mastering these calculations and understanding the interplay between logical addressing and physical routing is what separates basic connectivity troubleshooting from architecture-level network management. See you in the next lecture. Welcome back. In this chapter, we explore the standard TCP and UDP ports that define how network services communicate across modern infrastructure. To understand network connectivity, one must first distinguish between the Transmission Control Protocol, or TCP, and the User Datagram Protocol, or UDP. TCP is inherently connection-oriented, meaning it establishes a formal handshake between a client and a server to ensure that every packet sent arrives intact and in the correct order. If a packet is lost during transit, TCP handles the retransmission, which makes it the preferred protocol for data integrity. Conversely, UDP is connectionless and operates on a best effort basis without the overhead of a handshake or error correction. This lack of reliability is precisely why UDP is ideal for time-sensitive applications like video streaming or voice over IP, where losing a frame is preferable to delaying the entire stream while waiting for a retry. From an IT support perspective, Identifying whether a service communicates via TCP or UDP is often the first step in diagnosing why an application fails to connect through a strictly configured firewall or router. Web traffic relies almost exclusively on TCP to maintain sessions between browsers and servers. For unencrypted web content, we use port 80 for HTTP, though practically all modern traffic has migrated toward port 443 for HTTPS, which secures data using TLS encryption. File transfers involve a variety of ports based on the specific security requirements of the environment. Classic FTP uses port 21 for control and port 20 for data transmission. But because these are clear text, we rarely use them in secure production environments today. Instead, we favor SFTP, which runs over the secure shell protocol on port 22. Some specialized scenarios might still utilize TFTP on port 69, a connectionless UDP protocol often reserved for booting diskless workstations or transferring configuration files to network appliances because it lacks complex authentication mechanisms. Remote administration and email protocols form the backbone of day-to-day helpdesk operations. SSH, also on port 22, provides an encrypted channel for remote command line access, contrasting sharply with the aging and insecure Telnet protocol on port 23, which should be avoided in all modern deployments. When we look at mail, SMTP resides on port 25 for sending messages, whereas incoming mail retrieval uses the older POP3 on port 110 or the more modern IMAP, which uses port 143 to synchronize folders across multiple devices. Directory services often rely on LDAP on port 389, allowing systems to query centralized user databases. For Windows environments, the Remote Desktop Protocol, or RDP, is essential, and it communicates over port 3389 to provide users with a graphical interface into a host machine, assuming the firewall permits that specific traffic. Infrastructure management depends on critical background services that often go unnoticed until they stop functioning. DNS, typically running on port 53, is perhaps the most vital service in any network, as it translates human-readable domain names into the numeric IP addresses that routers and switches understand. DHCP uses ports 67 and 68 to automate the assignment of IP addresses to clients upon connection, ensuring that every machine has an identity on a local segment. Network monitoring often utilizes SNMP, which listens on port 161 for requests and port 162 for unsolicited traps or notifications sent from devices to management consoles. Finally, server message block, or SMB, which uses port 445, is the standard for file and printer sharing in Windows networks and is frequently the target of security restrictions due to its history of vulnerabilities. When troubleshooting connectivity, you will frequently need to verify which sockets are actually listening on a host machine. The netstat command is a powerful utility available on most operating systems that allows you to inspect active connections and the listening ports on a local host. By running a command like netstat with the proper arguments, you can see not only the port number, but also the state of the connection and the internal process that owns that port. This is invaluable when you find that a service is failing to start because another application has already bound itself to the required port. Understanding these sockets essentially provides you with a map of the network activity on a device, stripping away the abstraction and showing you the raw data flows moving through the system. Firewalls act as the gatekeepers for these ports, and they function by inspecting the headers of incoming and outbound traffic to enforce security policies. A stateless firewall examines individual packets in isolation, checking the port number against a predefined list of allowed services. A stateful firewall, however, is much more intelligent because it tracks the entire session state, ensuring that return traffic is only permitted if it corresponds to an actual request made from inside the network. When you're tasked with opening a port on a firewall, You're essentially telling the device to stop dropping packets destined for that specific port and service. This is a deliberate action that increases the attack surface of your host. So it is always architecturally sound to follow the principle of least privilege by only opening the minimum set of ports required for the application to function correctly. I will see you in the next lecture. Welcome to our exploration of networking infrastructure. In this section, we will examine the physical devices and transmission media that constitute the backbone of modern data networks. To understand networking hardware, one must first appreciate how we move data between nodes, starting with the evolution from hubs to switches. A hub operates at layer 1 of the OSI model, essentially acting as a multiport repeater that broadcasts every incoming packet out to every connected port regardless of the destination. This flooding behavior wastes bandwidth and creates significant collision domains, which is why hubs are considered obsolete in modern production environments. Bridges improve upon this by tracking MAC addresses to segment traffic, but they have largely been replaced by the modern switch. A switch functions at layer 2 and maintains a content-addressable memory table, allowing it to send data specifically to the port where the destination device resides. This process dramatically reduces congestion and ensures that bandwidth is utilized efficiently across the local area network. When looking at switches, it is important to distinguish between unmanaged and managed units, as they serve fundamentally different administrative needs. An unmanaged switch is a plug-and-play device that requires no configuration, making it suitable for simple office deployments where segmenting traffic is not a priority. However, in enterprise environments, we rely on managed switches that allow us to configure virtual local area networks, or VLANs. By implementing VLANs, we can logically isolate different departments or services on the same physical infrastructure, which enhances security and optimizes broadcast traffic control. These managed devices also support features like port mirroring for diagnostics and spanning tree protocol to prevent loops within the network topology. Mastery of these features is essential for anyone responsible for maintaining stable and secure network segments. While switches handle communication within a single network, routers are required to facilitate inter-network traffic, usually by bridging different subnets or connecting a local network to the internet. A router operates at layer 3 and makes forwarding decisions based on IP addresses rather than MAC addresses. It consults a routing table, which is a logic map that dictates where packets should be directed to reach their intended destination network. If the router does not have a specific path to a destination, it typically directs traffic to a default gateway, which is the exit point for the local network. This capability allows disparate networks, such as your office LAN and the global internet, to exchange data seamlessly. Understanding the routing table is a crucial skill when you're trying to diagnose why a client machine cannot reach external resources. Wireless infrastructure has shifted from simple access points to sophisticated systems managed by wireless controllers. A basic wireless access point, or WAP, simply provides a radio signal conversion for wired Ethernet traffic, allowing clients to connect to the network without cables. In larger environments, managing individual WAPs becomes tedious, so we use wireless controllers to manage the configuration, security, and handoffs from a centralized location. These controllers ensure that a client device can move physically between areas covered by different WAPs without losing connectivity, a process known as roaming. Security must also be strictly enforced at these points, often involving authentication mechanisms like Radius or modern WPA3 encryption standards. Proper placement and configuration are the primary factors in ensuring that your wireless coverage is both reliable and performant. Network security is effectively managed through the use of firewalls, which function as boundaries between trusted and untrusted zones. Stateful firewalls are the contemporary standard, as they inspect the state of active connections rather than looking at individual packets in isolation. When a user requests data, The stateful firewall records the connection details and allows the return traffic because it recognizes the transaction as part of an established session. In contrast, stateless firewalls operate based on static rules, verifying each packet individually against an access control list without regard for the broader communication context. While stateless devices can be faster due to their simplicity, they lack the contextual intelligence required to defend modern networks effectively against sophisticated threats. A well-designed firewall policy is your first and most effective line of defense against unauthorized access. Physical infrastructure relies heavily on the quality and type of cabling installed, with copper and fiber options serving different requirements. Cat5e is the absolute minimum standard today for gigabit Ethernet, though Cat6 is preferred for its better performance over shorter distances by reducing crosstalk. Cat6a further improves on this by supporting 10 gigabit Ethernet, making it the preferred choice for new structured cabling installations in offices. For long-distance or high-interference scenarios, we turn to fiber optics, which use light instead of electricity to transmit data. Single-mode fiber is optimized for long-distance communication as it carries a single ray of light, while multi-mode fiber uses larger cores to transmit multiple light modes for shorter, high-bandwidth connections. Selecting the correct cable type is critical for ensuring signal integrity over the life of the infrastructure. Proper termination using TIA/EIA 568A and 568B wiring standards is necessary to ensure consistent performance across the entire network. These standards dictate the pinout configuration for RJ45 connectors, and it is vital that both ends of a cable follow the same standard to avoid connectivity issues. When cables enter a data closet, they typically terminate into a patch panel, which acts as a bridge between the permanent wall cabling and the hardware in the rack. Behind the patch panel, wires are pressed into punch-down blocks using an impact tool to ensure a solid electrical connection. This organized approach allows IT personnel to move, add, or change network connections quickly by simply swapping short patch cables rather than disturbing the horizontal cabling infrastructure. Good cable management is the sign of a maintainable and professional data environment. Finally, physical layer troubleshooting requires specific tools to identify breaks or misconfigurations in the wiring. A crimper is used to attach connectors to the ends of copper cables, but its effectiveness depends entirely on the technician's ability to verify the end result. For this, we use a cable tester, which maps the individual pins to ensure that the wires are in the correct order and that there are no shorts or open circuits. When chasing a cable through a ceiling or wall, a tone generator and probe kit allow you to track a physical wire by emitting an audible signal on one end that is picked up by a probe at the other. These tools are the foundation of physical troubleshooting. Without them, you are essentially guessing at the source of connectivity issues. Consistent use of these specialized tools will turn a vague network problem into a clearly solvable technical task. I will see you in the next lecture. Welcome. In this chapter, we will explore the evolution of wireless standards and the critical security protocols required to protect modern network environments. Wireless communication relies on the IEEE 802.11 standard, which has evolved significantly to accommodate our increasing demand for bandwidth and speed. We began with the early versions like 802.11a and 802.11b, which established a foundation for operating on the 2.4 GHz and 5 GHz frequency bands. The transition to 802.11g provided a middle ground in terms of speed, but it was 802.11n that truly revolutionized throughput by introducing multiple input, multiple output, or MIMO technology. Following this, 802.11ac brought significantly wider channels and multi-user MIMO, solidifying 5 GHz as the performance standard in most environments. Recently, we have moved into the era of 802.11ax, also known as Wi-Fi 6, which emphasizes efficiency and density, particularly in crowded areas. Wi-Fi 6E further expands this architecture by opening up the 6 GHz spectrum, providing a massive amount of new, non-overlapping channels for high-performance devices. Understanding these standards is not just about knowing theoretical speeds, but about understanding the physical constraints and capabilities of the hardware you are supporting. When deploying wireless networks, the choice between frequency bands is fundamental to signal stability and performance. The 2.4 GHz band is historically crowded, as it is shared not only by older Wi-Fi devices, but also by Bluetooth signals, microwaves, and even cordless phones. Because there are only 3 non-overlapping channels in the 2.4 GHz spectrum, channels 1, 6, and 11. Interference is extremely common, leading to packet loss and high latency. In contrast, the 5 GHz band provides a much wider spectrum with a greater number of independent, non-overlapping channels, which inherently reduces contention between neighboring access points. While 5 GHz signals do not penetrate walls or floors as effectively as 2.4 GHz, they're essential for traffic-heavy applications like VoIP or high-definition streaming. As you design or troubleshoot these networks, you must consider the trade-off between the coverage range of 2.4 GHz and the raw performance of 5 GHz. Proper channel planning, where access points are configured on non-overlapping frequencies, remains the most effective mitigation strategy against performance degradation caused by co-channel interference. Security is an inseparable component of wireless administration, and the history of 802.11 security is a lesson in iterative improvement. WP, or Wired Equivalent Privacy, was our first major implementation, yet it is almost entirely broken due to short initialization vectors and flawed key management, meaning it should never be used in a production environment today. WPA was introduced as a stopgap measure, but it still relied on the vulnerable TCP encryption protocol. The introduction of WPA2 and the CCMP-S encryption standard significantly hardened our wireless networks, making brute force attacks computationally expensive and effectively impractical. Currently, WPA3 adds individual data encryption and stronger authentication, which helps protect against offline dictionary attacks, even when a user selects a weak password. When configuring a service set identifier, or SSID, you might encounter the option to hide your network broadcasts. While this might seem like a security measure, it is effectively obfuscation and does nothing to prevent advanced attackers from discovering your network. So I recommend focusing instead on robust encryption and strong authentication protocols. Authentication methods generally split into 2 distinct categories, with the simpler method being the pre-shared key, or PSK model. In this setup, every user shares the same password, which is convenient for home or small business use, but problematic in larger organizations where individual accountability is required. For enterprise environments, we rely on 802.1x authentication, which utilizes a radius server to verify the credentials of each individual against a centralized user database like Active Directory. This approach provides unique session keys for every user, which drastically improves security and simplifies access revocation when an employee leaves the company. Beyond internal access, we often encounter captive portals on guest networks, which provide a web interface for authentication or agreement to terms of service. Troubleshooting guest connectivity often involves clearing cache, resolving DNS redirection issues, or verifying that the client device has successfully received an IP address from the DHCP server after authentication. These scenarios require a clear understanding of the interaction between the client device, the access point, and the back-end authentication server or gateway. Optimal performance in a wireless network is rarely an accident. It is the result of careful environmental preparation. Conducting a site survey is the most reliable way to determine the ideal placement of access points, allowing you to account for building materials, reflective surfaces, and areas of high client density. During a survey, you assess signal strength, signal-to-noise ratios, in areas where potential interference might necessitate a change in channel selection or physical relocation of the equipment. When a user reports intermittent connectivity or weak signal strength, start your investigation by mapping their position relative to the nearest access point and checking for obstacles that could cause signal attenuation. In many cases, adding a new access point to fill a dead zone is superior to simply increasing the broadcast power of an existing one, as high power can lead to clients sticking to an access point despite a poor connection. By maintaining a logical, empirical approach to signal propagation, you can ensure a stable and performant wireless experience for all users on the network. See you in the next lecture. Welcome back. In this lesson, we will examine the various ways your computer connects to the broader internet and how those connections facilitate modern service delivery. To understand internet connectivity, we must first look at the infrastructure that physically carries data to your home or office. Digital Subscriber Line, or DSL, utilizes the existing copper telephone infrastructure to transmit data by operating on a frequency range separate for voice calls, which explains why you can browse the web while talking on a landline. Cable internet, conversely, uses the same coaxial infrastructure that delivers television signals, employing the data over Cable Service Interface Specification, or DOCSIS, to allocate bandwidth for data transmission. Fiber to the premise represents the current gold standard, using light signals transmitted through glass strands to achieve speeds orders of magnitude faster than copper or coax. While legacy technologies like dial-up, which relies on analog voice lines and inherently slow modem handshake speeds, or ISDN, an early attempt at digital telephony integration, are largely obsolete, they serve as the foundational chapters of how we transition to the broadband era. Understanding these distinctions is critical for an IT professional because bandwidth limitations, jitter, and reliability often correlate directly with the underlying medium being used by the client. Beyond wired infrastructure, wireless delivery mechanisms introduce their own set of constraints that you will frequently encounter in a helpdesk setting. Satellite internet is a common alternative for rural locations, yet it suffers from significant latency issues because the signal must travel to a geostationary satellite orbiting thousands of miles above the planet and back. Line-of-sight wireless, often used by smaller regional providers, requires an unobstructed path between the provider's transmitter and the user's antenna, making it susceptible to interference from foliage or new building construction. Cellular technologies have evolved rapidly from 3G to LTE and now 5G, providing high-speed mobile internet that increasingly competes with traditional fixed-line services. When a user reports connectivity troubles, distinguishing between these medium-specific limitations, such as a satellite connection's unavoidable lag versus a fiber connection's drop due to a physical line breach, is a fundamental diagnostic skill. You must always consider these environmental and technological factors before assuming a configuration error exists within a local hardware or software environment. When we classify the scope of these connections, we typically categorize them into specific network types based on their geographic reach. A personal area network, or PAN, describes the small-scale connection between devices, such as your smartphone tethering to a Bluetooth headset or a laptop. As we move outward, a local area network, or LAN, encompasses the private network within your office or home, typically managed by a router that assigns private IP addresses to every connected client. A wide area network, or WAN, connects these smaller networks across larger distances, effectively serving as the backbone that joins the global internet together. A critical component in managing this traffic across insecure public networks is the virtual private network, which employs tunneling protocols to encapsulate data, ensuring that remote traffic remains encrypted and authenticated as if it were on a local network. Properly leveraging a VPN is a prerequisite for secure remote work, directly impacting how modern businesses protect their information assets while providing flexibility to their field personnel. The maturation of these network connections has given rise to the modular delivery of software and computing resources collectively categorized as cloud services. Software as a service, or SaaS, allows users to access applications like word processors or CRM systems through a web browser, offloading installation and maintenance to the provider. Infrastructure as a service, or IaaS, offers virtualized computing resources such as servers and storage, essentially renting out the hardware layer so that your organization does not need to maintain a physical data center. Platform as a service, or PaaS, sits in the middle, providing a development environment that handles the operating system and middleware, allowing developers to focus solely on building and deploying code. Furthermore, cloud storage providers utilize these connections to synchronize files across multiple devices, often complicating troubleshooting when a user's local changes fail to propagate during an internet outage. Familiarity with these service models allows you to identify whether an issue resides within the application portal, the underlying platform configuration, or the end user's local network connectivity. See you in the next lesson. Welcome to the chapter on operating system deployment, where we will cover everything from hardware prerequisites to post-installation configuration. This section is designed to provide you with a systematic approach to managing and deploying modern operating systems in professional environments. When preparing for an operating system installation, the first objective is to verify that the underlying hardware meets the vendor's minimum specifications. For Windows 11, for example, technical requirements like TPM 2.0 and Secure Boot are mandatory, whereas Windows 10 is more permissive regarding older hardware. macOS hardware requirements are strictly dictated by the EFI firmware and the specific model year of the Mac, which often involves checking if the provided hardware has reached the end of its supported lifecycle. Before you begin any installation, you must check the official documentation for the specific version of the OS you intend to deploy. Ignoring these hardware thresholds will often lead to failed installations or worse, latent instability that becomes difficult to troubleshoot later in the support lifecycle. Always ensure that the processor architecture, RAM capacity, and disk space are sufficient to support not just the base OS, but the applications that the end user intends to run. Validating these constraints saves you from the frustration of a system that boots but performs at unacceptable speeds due to hardware deficiencies. The choice between a clean installation and an in-place upgrade is a fundamental decision that dictates the integrity of the resulting environment. A clean installation completely erases the contents of the target storage drive, creating a blank slate where the OS can build a stable registry and file structure from the ground up without legacy clutter. Conversely, an in-place upgrade attempts to preserve a user's applications, settings, and documents by overwriting the existing OS files while keeping the data partition intact. While in-place upgrades are convenient for standard users, they carry the risk of carrying over corrupted registry keys or incompatible driver conflict from the previous installation. In professional settings, a clean install is generally preferred to ensure a predictable environment, whereas in-place upgrades are reserved for scenarios where user downtime must be strictly minimized. By understanding when to deploy each method, you can better manage user expectations and reduce the likelihood of post-deployment support tickets. Modern boot methods allow administrators to deploy OS images across a wide array of scenarios, ranging from single workstation setup to massive enterprise rollouts. Booting from a USB drive is the standard for local deployment, where you use tools like the Windows Media Creation tool to burn an ISO onto a flash drive and boot from it by overriding the BIOS/UEFI boot order. For larger environments, PXE, Pre-Boot Execution Environment, boot is the preferred solution as it allows a computer to pull an OS image directly from a network server without the need for physical media. ISO mounts are primarily used within virtualized environments, where you can attach a disk image file directly to a running virtual machine to simulate a boot event. Each of these methods serves a distinct purpose, and your familiarity with selecting the appropriate boot target during the post sequence is an essential diagnostic skill. Disk organization requires an understanding of both partition schemes and file system formats to ensure compatibility and performance. The legacy master boot record (MBR) scheme, which is limited to 4 primary partitions and drives up to 2 terabytes, has largely been replaced by the GUID partition table (GPT) scheme. GPT supports significantly larger volumes and is a prerequisite for modern UEFI-based systems, offering improved data integrity through CRC checks. Once you have defined a partition scheme, you must format the volumes using an appropriate file system, such as NTFS for standard Windows data or APFS for modern macOS environments. While FAT32 is useful for cross-platform compatibility with external drives due to its universal support, its inability to handle files larger than 4 gigabytes makes it unsuitable for hosting an entire operating system. exFAT is a modern alternative that provides the high-capacity support of NTFS while maintaining better cross-platform compatibility. Post-installation tasks represent the final bridge between a functional OS and a productive workstation. Immediately after the initial setup completes, the priority is to execute Windows Update or the equivalent platform-specific utility to patch known security vulnerabilities and finalize system files. Essential drivers must then be verified in the device manager to ensure that specialized hardware components like network interfaces, graphics cards, and sound controllers are operating correctly. It is also common practice to configure regional settings, including time zones and keyboard layouts, to align with organizational standards and user needs. Furthermore, you'll need to determine whether the workstation should be joined to a Microsoft account for cloud-integrated services or kept as a local account for simplified offline management. Mastering these individual steps ensures that the system you hand over to the user is stable, patched, and uniquely configured to their operational requirements. When transitioning users between machines, moving their data is often the most sensitive part of the administration process. Tools like the User State Migration Tool, USMT, allow administrators to capture user settings, desktop configurations, and document files from one system and recreate them on another. This approach avoids the inefficiency of manual file copying and ensures that the user experience remains consistent despite the platform or hardware change. In scenarios where you need a sandbox for testing, dual boot configurations, or dedicated virtual machines offer a safe way to run multiple operating systems concurrently on the same hardware. Dual booting splits the physical disk into distinct partitions for each OS, whereas virtualization encapsulates the entire OS inside a container running as a guest on your primary system. Understanding these migration and virtualization concepts allows you to offer more sophisticated support, especially when dealing with legacy software dependencies that require older, specifically configured environments. See you in the next lecture. Welcome to this chapter, where we shift focus toward the command line interface and the automation scripts that serve as the backbone of efficient system administration. We will explore how to master Windows and Linux environments through direct terminal interaction to troubleshoot and manage systems. When we interact with a computer, we often rely on graphical user interfaces, but those layers of abstraction eventually hide the precision required for deeper diagnostics. The Windows Command Prompt, or CMD, remains a critical tool for any IT professional because it provides direct access to the operating system's networking stack and file management utilities. When you use the IP protocol configuration command, you are not merely viewing a text summary. You're querying the TCP IP stack configuration, revealing exactly how an NC communicates with a local network. Similarly, tools like Ping and Tracert allow you to quantify latency and identify the specific hop where a network connection fails, which is far more reliable than waiting for a browser to time out. Even when the graphical interface is unresponsive or corrupted, tools like SFC/ScanNow and CheckDisk provide a way to verify system integrity and disk health from a recovery environment. Understanding these commands turns the terminal into a diagnostic laboratory rather than just a place to type text. Navigating the file system through a terminal requires understanding basic commands like cd for changing directories and dr to list their contents. In a production environment, you will often find yourself needing to jump between folders rapidly without the visual overhead of an Explorer window. While these commands seem rudimentary, they're the foundation for more advanced operations, such as piping output into text files or scripts. When you move to the Linux terminal, you'll find analogous commands such as ls, which serves the same listing purpose as dr, and cd, which retains its same functional role. However, Linux introduces the concept of permission management using chmod, which dictates read, write, and execute privileges at a granular level. Furthermore, the sudo command acts as a gateway to administrative privileges, ensuring that only authorized users can perform system-wide changes. Automation is the true leverage point for any IT support role, moving us from manual repetition to scalable management. We start this automation journey with Windows batch files, which use the .bat extension to group a series of CMD commands into a single executable process. While batch scripting is somewhat limited by the legacy syntax of the command prompt, it remains functional for simple administrative tasks like mapping network drives or clearing temporary caches periodically. To reach a higher level of control, we turn to PowerShell, the industry-standard environment for task automation and configuration management. PowerShell is built on top of the .NET framework, meaning it treats system objects, not just text, as its data units. This object-oriented approach allows you to manipulate system settings, user groups, and services with a level of precision that batch files simply cannot replicate. As you begin writing PowerShell scripts, you must understand execution policies, as they serve as the primary security layer to prevent the unintended running of malicious code. By default, many Windows environments restrict script execution, requiring you to explicitly set a policy that balances your operational needs with system security principles. Transitioning from Windows to Linux, you will encounter the shell script, typically identified by the .sh extension, which operates on a different set of logic and syntax conventions. Shell scripting in environments like Bash relies on utility suites like grep, which allows you to parse through massive log files with incredible speed to locate specific error strings. Whether you're using PowerShell to automate a large-scale user deployment or Bash to scan logs on a server, the philosophy remains the same. Define the task in code, test the logic, and let the interpreter handle the execution. These skills directly translate into remote management capabilities, allowing practitioners to connect to distant systems and resolve corruption or configuration errors without needing physical access to the hardware. See you in the next lesson. Welcome back. In this chapter, we will explore the essential Windows administrative and management tools that allow an IT professional to diagnose, configure, and maintain a functional operating system environment. Understanding the distinction between the legacy control panel and the modern Windows Settings app is the first step toward effective system navigation. While the control panel acts as a collection of advanced applets rooted in heritage Windows architecture, the Settings app provides a unified, mobile-friendly interface for common user-level configurations. You will often find yourself jumping between both because some granular network or user management tasks remain exclusive to the classic control panel applets. Keeping a mental map of where specific settings reside reduces the time spent searching for configurations during a high-pressure support call. Whenever you are faced with a configuration task, look for the most specific path first before defaulting to the broadest category in the settings menu. Task Manager is arguably your most vital tool for real-time performance monitoring and reactive troubleshooting. When a user reports that their system has become sluggish or unresponsive, pressing Control-Shift-Escape provides instant visibility into CPU, memory, and disk utilization metrics. Beyond simple statistics, the Details tab allows you to inspect specific process IDs and terminate applications that have hung or are consuming system resources unfairly. Always prioritize identifying the service or process responsible for the resource spike rather than simply killing processes at random, which can lead to system instability. Effectively navigating the Startup tab can also help you identify and disable bloatware that consumes unnecessary CPU cycles upon login. Device Manager serves as the primary interface for managing hardware drivers and resolving physical device communication conflicts. If a peripheral or internal component fails to respond as expected, the first indicator is usually a yellow exclamation mark icon within this utility. By examining the properties of a device, you can roll back a problematic update a driver from a local manufacturer repository, or completely uninstall a device to force the operating system to re-recognize it on the next initialization. It is important to treat drivers as the bridge between software requests and hardware execution, as corrupted code here is the most common cause of blue screen of death, errors, or hardware timeouts. Always check the device status for specific error codes provided by the kernel, as these codes directly pinpoint whether the issue is a resource conflict or a missing firmware file. When it comes to storage, disk management provides the necessary control to create partitions, assign drive letters, and initialize new physical drives. You will frequently interact with this tool to shrink partitions for dual boot configurations or to verify that a drive has been assigned a mount point in NTFS formatting. Understanding the file system structure is critical here, as an incorrectly formatted drive will not appear in the File Explorer despite being detected by the motherboard. By monitoring disk health indicators within this interface, you could distinguish between simple logical partitioning errors and genuine physical disk failures. Always ensure you have backed up any critical local data before attempting to modify volume structures, as partition manipulation carries a risk of data loss. The Event Viewer acts as the central repository for every diagnostic message, warning, and critical error generated by the Windows kernel or installed applications. When a system reboots unexpectedly or a service fails to initialize, you must learn to read through the system and application logs to find the correlation between the timestamps and the reported errors. Each entry provides an event ID, which serves as a search index for finding community source solutions to specific software crashes. It is a mistake to approach these logs without a systematic mindset, as the sheer volume of information can easily lead to distraction. Filter your log views by severity level to prioritize the errors that immediately impact system stability while ignoring the informational noise. Managing services through the services.msc console is essential for controlling the background processes that power core Windows functionality. Many system problems, such as a printer failing to reach a network queue or an update agent hanging indefinitely, stem from a service that has entered a stopped or orphaned state. Identifying the startup type, automatic, manual, or disabled, allows you to troubleshoot why a feature is not functioning during the boot cycle. If you need to restart a service, always evaluate dependencies first, as stopping one base service might inadvertently disable a dozen other related background processes. This granular control is what separates an amateur user from a professional technician who understands the precise mechanisms of the operating system. Finally, you should familiarize yourself with advanced auditing tools like System Information and the Registry Editor. MSINFO 32 acts as a comprehensive summary of your hardware, firmware versions, and driver assignments without requiring you to navigate through individual device properties one by one. Conversely, the Registry Editor is a powerful but dangerous database that stores almost every configuration state for the operating system and applications. You will operate within HKY_local_machine for configurations applicable to all users, and HKY_current_user for settings personalized to the currently logged in account. Never modify registry entries without first exporting a backup of the affected hives, as a single mistyped character can render the operating system unbootable. See you in the next lecture. Welcome to the chapter on user account and policy management. We will explore how to secure systems through access control, policy enforcement, and identity management. Managing user accounts effectively begins with understanding the principle of least privilege, which dictates that users should only possess the minimum level of access required to perform their job. In a local environment, this involves managing local SAM databases, while Active Directory introduces centralized identity management using objects within a domain. A standard user account is the default for daily operations because it prevents unauthorized modification of system files or the installation of malicious software. Administrators hold elevated privileges and must handle these credentials with caution to avoid accidental or intentional damage to the system. User account control acts as a checkpoint for these elevated actions, prompting for authorization whenever a process requests administrative-level changes to the operating system configuration. Group policy objects serve as the primary mechanism for enforcing enterprise-wide configurations in a domain environment. By applying policies at the site, domain, or organizational unit level, an IT administrator can mandate password complexity, enforce screen lock timeouts, or restrict access to control panels. These settings are inherited by child containers unless inheritance is explicitly blocked, a concept fundamental to hierarchical management. When troubleshooting account issues, you will frequently handle situations involving locked accounts, often due to excessive failed login attempts. Resetting passwords requires verifying the user's identity through established protocol, as improper handling can lead to unauthorized access. Always ensure that account lockout thresholds are balanced to provide security against brute force attacks without creating excessive administrative overhead from frequent user lockouts. Access to shared resources relies on a bifurcated permission structure involving both share permissions and NTFS permissions. Share permissions control access over the network, effectively acting as the first gate, while NTFS permissions provide granular control over files and folders on the local disk. The effective permission is always the most restrictive combination of the two, meaning both must be satisfied to access a resource. Inheritance is the default behavior, where child objects automatically receive the access control list from their parent folder, though you can disable this to customize specific needs. When managing remote desktop protocol access, you must also be mindful that local group membership dictates who can establish a remote session. Auditing plays a vital role here, as it records access events to the security logs, providing the necessary trail for compliance and forensic analysis when investigating unexpected resource access. See you in the next lecture. Hello, and welcome to this session focusing on the maintenance and troubleshooting of software environments. In this chapter, we will master the essential skills required to keep applications stable, secure, and performant for your users. Software troubleshooting begins with understanding the life cycle of an application, from the initial installation phase to the inevitable point of degradation. When an application crashes, it often stems from corrupted binaries, missing dependencies, or conflicting configuration files. The first step in remediation is to utilize the built-in repair functionality provided by the installer, which evaluates the local installation against the expected state and replaces missing files. If a repair fails, a full uninstallation followed by a registry-level cleanup is often necessary to remove lingering configurations that might prevent a clean reinstall. For legacy applications that were never intended for the current version of the operating system, the compatibility mode settings allow you to simulate older environments by adjusting system calls and API behaviors. Always verify that you are running the installer with elevated administrative privileges, as many installation errors are simply a byproduct of failed write operations to protected system directories. System performance is frequently hindered by the accumulation of startup items that consume memory and CPU cycles before the user even interacts with the machine. Managing these processes requires a careful look at the startup folder and the registry keys that trigger applications upon logon. Modern operating systems provide task management utilities where you can disable non-essential startup entries without necessarily uninstalling the software. Beyond startup management, routine maintenance tasks such as temporary file removal are critical for long-term stability. While modern solid-state drives do not require defragmentation, traditional mechanical hard drives benefit significantly from periodic defragging to prevent excessive disk head movement. Furthermore, the systematic clearing of browser caches and cookies is the most effective first response to intermittent web application errors, as it forces the browser to refetch the latest content and state from the server. Licensing is a central concern for IT support, as it dictates the legal and technical boundaries of software deployment. OEM licenses are tied to the specific hardware on which they were initially activated and cannot be transferred to a new machine, making them a common choice for pre-built workstations. Retail licenses, by contrast, offer more flexibility, allowing the user to move the software to different hardware upon retirement of the original system. Volume licensing is designed for enterprise environments, providing a centralized way to manage product keys and activate multiple machines through a single agreement or activation server. Subscription models represent a significant shift, relying on cloud-based authentication to grant time-limited access to software, which necessitates constant internet connectivity for periodic validation. Understanding these distinctions ensures that your department remains compliant with vendor policies while avoiding the service interruptions associated with activation failures. The landscape of modern IT support relies heavily on managed patches to mitigate the vulnerabilities inherent in software. Unpatched third-party applications provide low-hanging fruit for malicious actors, which is why your patching strategy must be both proactive and consistent. You should prioritize security updates over feature upgrades, as the former close doors that are actively being exploited by various threats. When an application behaves unexpectedly despite these maintenance efforts, the built-in Windows troubleshooters can automate the process of identifying configuration drifts or missing drivers. These wizards are specialized diagnostic tools that scan system states against known problem patterns and suggest automated fixes. Effective browser management also extends to handling extensions and proxy configurations, as misconfigured proxies act as silent blockers for network traffic to and from legitimate services. See you in the next lecture. Welcome to this new chapter where we will explore the foundational concepts of virtualization and cloud computing that modern IT environments depend on. By the end of this section, you will understand how to manage virtual workloads and navigate the complexities of cloud-based infrastructure. Virtualization fundamentally changes how we utilize physical hardware by decoupling the operating system from the machine itself. At the heart of this technology sits the hypervisor, or virtual machine monitor, which allocates physical resources like CPU, memory, and storage to individual virtual machines. A Type 1 hypervisor, often called bare metal, runs directly on the server's physical hardware without an underlying host operating system. This architecture is common in data centers because it offers superior performance and security by minimizing the management overhead. Conversely, a Type 2 hypervisor runs as an application on top of an existing operating system, like Windows or Mac OS. While Type 2 hypervisors are less efficient for enterprise production, they are excellent tools for developers or home users who need to test software in isolated environments. Regardless of the type, virtualization provides the critical benefits of resource pooling, which allows multiple virtual machines to share the same physical hardware efficiently. It also ensures strict isolation between environments so that a crash in one instance does not compromise the host system. Snapshotting capability further enhances this ecosystem by allowing administrators to capture the state of a virtual machine at a specific moment in time so that they can quickly revert to a known good state after an update or a configuration change. Before you can run a virtual machine on a local workstation, you must often enable hardware-assisted virtualization through the computer's BIOS or UEFI settings. These features are known as Intel VDX or AMD depending on your processor architecture. Enabling these extensions allows the hypervisor to interact directly with the CPU features required to manage guest operating systems reliably. If these settings remain disabled, the performance of your virtual machines will be abysmal, or they may fail to start entirely. Once virtualization is enabled, you might encounter the distinction between thin and thick clients in a virtual desktop infrastructure deployment. A thick client is a computer that provides rich functionality and can perform processing tasks independently even if the network connection breaks. In contrast, a thin client is a minimalist terminal designed primarily to connect to a server where the actual computing occurs. Implementing VDI for remote workers relies on these infrastructure concepts to centralize desktop management while allowing employees to access their workspace from anywhere. This centralized approach simplifies security because user data stays within the data center, yet it requires careful network planning to ensure a smooth user experience. The cloud computing landscape is structured around several distinct deployment models that dictate how you manage your data and infrastructure. Public clouds offer services over the internet with shared infrastructure, which provides high scalability but less granular control over hardware. Private clouds provide a more exclusive environment, often hosted on premises or in a dedicated data center, offering maximum control and security for sensitive information. Hybrid cloud environments bridge the gap by connecting private and public infrastructure, allowing organizations to maintain flexibility while keeping critical systems sequestered. Community clouds serve specific groups with shared requirements or compliance mandates, such as government or healthcare organizations, acting as a collaborative pool of resources. These models are governed by the shared responsibility model, which clarifies that the provider is responsible for the security of the cloud infrastructure, while the customer remains responsible for the security of the data and configurations within their virtual environments. Cloud services also introduce rapid elasticity to scale resources up or down based on demand, which is complemented by on-demand self-service that lets users provision capacity without manual intervention from IT staff. Troubleshooting cloud storage requires a systematic approach to identifying where the connectivity chain fails. Start by verifying local network settings to ensure the workstation can reach the cloud provider's API endpoints or gateway addresses. If DNS resolution fails, the local machine cannot map the cloud storage service to a reachable network address. It is also important to check for firewall restrictions or proxy settings that might be intercepting or blocking traffic to storage services like Amazon S3 or Microsoft Azure. When it comes to newer deployment concepts, it is vital to distinguish between virtual machines and containers. While virtual machines encapsulate an entire operating system along with the application, containers share the host operating system kernel and isolate only the application process itself. Containers are significantly more lightweight and faster to deploy than virtual machines, which makes them ideal for microservices and cloud-native application development. However, containers do not provide the same degree of strong hardware-level isolation that virtual machines offer if you require distinct kernel versioning or high-security partitioning. Understanding how to manage these disparate environments is a characteristic skill of modern systems administration. I will see you in the next lecture. Welcome to the chapter on troubleshooting theory, where we will adopt a structured methodology to resolve any technical challenge you might encounter. We will discuss the industry-standard 6-step troubleshooting process that separates reactive guessing from effective, professional technical support. In IT support, the difference between a seasoned professional and a frustrated novice is often the presence of a structured mental framework. When a machine fails to boot or a user loses network connectivity, our instinct is frequently to start changing settings randomly, hoping one of them sticks. This is what we call falling down a rabbit hole, and it is the most effective way to waste time and create new, unforeseen problems. The CompTIA's six-step troubleshooting process is designed to prevent this chaotic behavior by imposing a rigid, logical structure on the diagnostic workflow. It applies equally well to a faulty power supply, a corrupted operating system registry, or a complex routing issue on a Cisco switch. By following these steps consistently, you ensure that you arrive at a solution in the shortest possible time while minimizing the risk of causing collateral damage to the system. The first step is identifying the problem, which is an exercise in data gathering and active listening. Resist the urge to start pulling cables or booting into safe mode before you have fully understood the scope of the issue from the user's perspective. Ask the user open-ended questions about what they were doing when the failure occurred and document any error messages appearing on the screen. It is equally important to examine system logs, like the Windows Event Viewer or network diagnostic outputs, to separate the user's subjective report from objective system data. Once you have a clear picture of the symptoms, avoid jumping to conclusions immediately, as human error often masks underlying technical failures. Establishing these ground facts prevents you from chasing ghosts and keeps your diagnostic efforts focused on the actual reported behavior. Once you have identified the problem, the second step is to establish a theory of probable cause. In many cases, the most likely solution is also the simplest, which is why we always follow the principle of testing the obvious first. If a peripheral device is not working, check the power cable before you suspect a driver conflict or a motherboard failure. For network issues, verify the physical connectivity before you start rewriting IP configurations or routing tables. By ordering your theories from the simplest to the most complex, you can resolve the majority of common issues without spending hours on deep diagnostics. This is not about guessing. It is about statistically narrowing down the possibilities based on the symptoms identified in the first step. After theory formulation comes the third step, which is testing the theory to verify the root cause. This requires you to isolate the variable you suspect is causing the problem and change only that one factor at a time. If your change does not resolve the issue, you must revert the system to its previous state before testing your next theory. Failing to revert changes creates a chaotic environment where you no longer know what is causing the error. If your theory is proven incorrect through testing, discard it, stop blaming that component, and move on to the next probable cause on your list. This rigorous scientific approach is what keeps an IT professional productive, even when facing an unfamiliar or intermittent problem. The fourth step involves establishing a plan of action and implementing the solution, which requires a focus on systemic impact. Before applying a fix, consider if the resolution might disrupt other services or if it requires specific permissions or scheduling. For example, updating firmware or replacing a critical piece of hardware requires careful planning to avoid unnecessary downtime for the user. Once the plan is ready, execute it methodically and remain attentive to the system's behavior during the implementation. If the solution proves to be more complex than initially anticipated, escalate the issue to a senior administrator rather than forcing a fix that could exacerbate the primary fault. Professionalism dictates that you know your limits and prioritize the integrity of the computing environment over the speed of the fix. Step 5 is verifying full system functionality and implementing preventive measures to ensure the problem does not repeat. It is not enough that the immediate error has cleared. You must ensure that all related services are still operational and that the user can perform their core tasks without hindrance. If you have replaced a failed component, perform stress tests or log checks to verify that the replacement is performing within acceptable parameters. When you confirm the system is healthy, take a moment to consider what preventive actions can be taken, such as updating security policies, refreshing drivers, or automating a backup task. This transition from reactive troubleshooting to proactive maintenance is what builds long-term system stability and reduces the volume of future support tickets. The final and most overlooked step is documenting your findings, actions, and outcomes for future reference. Documentation is not just red tape. It is a critical repository of institutional knowledge that prevents you and your colleagues from having to solve the same problem twice. Record exactly what the symptoms were, which theories were tested, what the final solution was, and any preventive measures taken. When you encounter a similar issue months later, you'll be able to retrieve this information instantly, drastically reducing your mean time to resolution. Treating documentation with the same importance as the physical repair ensures that you are continuously improving your skill set and helping your team grow more efficient as a unit. See you in the next lecture. Welcome to this chapter on network troubleshooting, where we will master the diagnostic techniques required to resolve connectivity failures and performance bottlenecks. We are going to explore the practical tools and methodologies essential for maintaining robust network stability in a professional environment. When a user reports a loss of connectivity, the first logical step involves ruling out physical layer failures before diving into complex protocol debugging. Examine the network interface card link lights on the workstation and the corresponding status indicators on the network switch to verify electrical signal integrity. A steady green or amber light typically suggests a functional physical connection, whereas a complete lack of activity often points to a faulty patch cable or a deactivated switch port. In environments where the hardware status remains ambiguous, utilizing a physical loopback plug allows you to test the integrity of a network port by creating a closed circuit. This hardware diagnostic tool sends a signal out of the interface and monitors for an immediate return, effectively determining if the port hardware is capable of transmitting and receiving data. While physical verification addresses the foundation of your network stack, most modern issues reside higher up within the logical configuration of the operating system. Connectivity problems frequently manifest as IP configuration errors, often identified by the presence of an APIPA address starting with 169.254.x.x. When a computer fails to obtain a valid lease from a DHCP server, the operating system assigns this local link address as a fallback mechanism, which prevents the host from communicating outside its immediate subnet. One common cause for this behavior is DHCP scope exhaustion, which occurs when a network segment runs out of available IP addresses to assign to new devices. Before assuming a server failure, check if the client is encountering an IP conflict, where two devices on the network have been manually assigned the same static address. Use the ping utility to verify host-to-host connectivity by sending ICMP echo request packets to a target, noting that a successful response confirms basic routing and interface functionality. If you consistently receive a destination unreachable message, you must investigate the gateway configuration to ensure the device knows how to reach external networks. When basic ICMP tests succeed, but specific services fail, we shift our focus to DNS resolution and potential routing bottlenecks. Then SLOOKUP utility serves as the primary tool for verifying that your local DNS resolver is capable of translating a domain name into its corresponding IP address. If SLOOKUP returns a timeout or an incorrect record, the issue likely resides within your DNS infrastructure rather than the physical medium. For performance issues where a connection exists but feels sluggish, the tracer command becomes invaluable as it maps each individual hop between the source and destination. By analyzing the time to live value, you can observe how packets descend through the network topology until they hit a congested router or a misconfigured firewall. If a specific hop consistently shows high latency or packet loss, you have identified the exact point of contention within the infrastructure. Wireless environments present a distinct set of diagnostic challenges compared to tethered connections because signal strength and interference are dynamic variables. Wireless interference caused by overlapping channels, physical obstructions, or competing electronic devices often leads to frequent signal drops and erratic throughput. To mitigate these issues, you should monitor the signal-to-noise ratio and ensure that access points are placed in optimal locations relative to the end users. Aside from physical interference, Troubleshooting VPN connections requires a deep understanding of tunnel authentication, encryption handshakes, and NAT traversal rules. If a user cannot establish a secure tunnel, verify that the remote gateway is reachable and that the client software is not blocked by local security policies or firewall rules that discard encapsulated traffic before it can be processed. At the deepest level of technical analysis, you may find it necessary to capture and inspect raw traffic to solve persistent network instability. Wireshark provides a granular view of every packet traversing a network segment, which is particularly effective for identifying broadcast storms that saturate available bandwidth. A broadcast storm manifests as a sudden, massive increase in the volume of ARP requests or other broadcast traffic, often caused by a switching loop or a malfunctioning network card. By analyzing these packet captures, you can pinpoint the offending device by following the source MAC address, allowing you to isolate and disable the segment contributing to the congestion. This level of packet-level inspection acts as the final tier of troubleshooting when logs and administrative tools provide insufficient evidence of a root cause. Applying these structured diagnostic steps consistently ensures that you can systematically reduce the time it takes to restore services to the end users. I will see you in the next lesson. Welcome back. In this chapter, we will explore the essential principles of security and the methodical approach required to identify, neutralize, and remediate malware infections within an enterprise environment. Malware manifests in predictable ways that you must learn to recognize immediately. A sudden spike in system latency, the appearance of intrusive pop-up advertisements, or unauthorized modifications to files often signal an underlying compromise. These symptoms indicate that malicious code is competing for system resources or attempting to exfiltrate private data. Viruses differ from worms because the former requires human intervention to execute, whereas worms can replicate independently across a network architecture. Trojans disguise themselves as legitimate software, tricking users into installing a malicious payload that provides backdoors for attackers. Ransomware represents a more aggressive threat, encrypting user data to extort payment, while spyware operates silently to harvest keystrokes and browser history for illicit gain. Understanding these distinct threat models allows you to select the appropriate defensive tools and remediation strategies during an incident response event. Attackers often bypass technical controls by targeting the human element through various forms of social engineering. Phishing remains the most prevalent technique, involving deceptive emails meant to harvest credentials or distribute malicious links. Tailgating is a physical security breach where an unauthorized individual follows an authorized person into a restricted area, circumventing badge readers or manual door locks. Shoulder surfing is equally dangerous, as it involves the surreptitious observation of a user entering passwords or viewing sensitive information on a public monitor. These tactics succeed because they exploit human tendencies toward trust and convenience rather than technical vulnerabilities. You must understand how to detect these attempts to advise users on how to maintain situational awareness. Preventing these breaches is vastly more efficient than attempting to reverse the damage caused by a successful social engineering attack. When an infection is confirmed, you must follow a disciplined 7-step remediation process to ensure the threat is permanently eliminated. First, you must identify the infection by documenting symptoms and verifying that the system is actually compromised by malicious software. Next, isolate the infected machine from the network to prevent horizontal movement or lateral propagation of the malware to other critical infrastructure. Once isolated, disable System Restore to ensure that malicious files are not backed up or restored during the cleaning process. Then, proceed to remediate the system by updating your antivirus definitions and executing a full, deep scan to remove the detected threats. After the scan cleans the malware, you should schedule future automated scans to monitor for any secondary infections or deep-seated rootkits. Only after you're confident that the system is clean should you re-enable System Restore to establish a new, legitimate recovery point. Finally, take the opportunity to educate the user on the circumstances that led to the infection so they can avoid similar practices in the future. Effective defense requires a layered approach beyond just running antivirus software on individual end-user workstations. You must configure firewalls to enforce strict inbound and outbound traffic policies, ensuring that only necessary ports remain open to the public internet. Antivirus and anti-malware definitions must be updated daily, preferably through a centralized management server, to ensure all clients have most recent threat intelligence. Beyond software, password policies must mandate complexity and frequency of rotation to limit the utility of compromised credentials. Multi-factor authentication adds a critical security layer by requiring a secondary verification method, effectively neutralizing the impact of a stolen password. Always encourage the use of physical security measures, such as privacy screens that obscure a monitor from passersby and cable locks that physically tether hardware to a desk. These measures collectively decrease the overall attack surface and empower the user to participate in the security posture of the organization. I look forward to discussing the next section with you shortly. Welcome to this chapter, where we will examine the soft skills and procedural discipline necessary to thrive as an IT support professional. We will explore everything from professional communication and documentation standards to the critical safety and compliance protocols that define a responsible technician. In an IT support environment, technical expertise is only half of the equation, as your ability to communicate effectively often determines your success. Professionalism starts with active listening, which means you must refrain from interrupting the user and instead focus on gathering the necessary details to formulate a solution. When you communicate with users, you must calibrate your language based on their technical literacy to avoid unnecessary confusion. Using heavy technical jargon with a non-technical end user can alienate them and obscure the information you need to resolve their issue. Conversely, speaking in overly simple terms to an experienced system administrator may come across as condescending or unproductive. You should aim to be precise and clear, ensuring that the user understands the progress of their issue and the steps you're taking to rectify it. Documentation within systems like ServiceNow or Zendesk is the cornerstone of this professional interaction because it serves as the historical record of the organizational infrastructure. A well-written ticket provides clear context, a description of the troubleshooting steps already performed, and a detailed summary of the final resolution provided. Managing difficult customers or high-pressure situations is an inevitable part of the job, and your ability to maintain composure is a core professional competency. If a user is frustrated, let them speak without interruption, acknowledging their concerns without immediately debating the technical validity of their complaint. Once they have expressed their frustration, move the conversation toward de-escalation by focusing on objective problem solving rather than taking accusations personally. Explain the steps you're taking to address their problem, as transparency often reduces the anxiety that leads to impatience. If a situation escalates beyond your capacity or the user becomes abusive, rely on your established organizational escalation procedures to pull in a supervisor or HR if necessary. Never compromise your personal safety or professional integrity to appease an angry customer. Maintain a steady, calm, and professional demeanor regardless of the underlying emotion of a user, as this establishes you as a reliable point of stability in the organization. Safety protocols represent the professional boundary between an effective technician and a liability for the company. When handling heavy equipment, such as server chassis or heavy laser printers, always use proper lifting techniques by bending at your knees and keeping your back straight to prevent injury. Electrical hazards are equally significant, so you must always power down devices and disconnect power sources before opening cases or interacting with internal components. Toxic materials, including spent printer toner or degraded lithium-ion batteries, require specific disposal protocols to minimize environmental impact and health risks. Never discard batteries or toner in standard trash bins, as they can cause chemical leaks or ignition if handled incorrectly. You are responsible for knowing the local regulations regarding electronic waste, or e-waste, to ensure the components are recycled through authorized facilities. This is not just a personal safety imperative. It is a regulatory requirement that keeps your organization compliant with environmental standards. Behind every successful IT operation lies a structured approach to record-keeping, compliance, and disaster resilience that ensures business continuity. We must discuss data protection regulations like HIPAA, GDPR, and PCI-DSS, which dictate how we handle personal health information, European citizen data, and payment card details respectively. These regulations require strict documentation, access control, and audit trails for every piece of sensitive information stored on your systems. Disaster recovery strategies revolve around the frequency and types of backups being performed, which include full, incremental, and differential methods. A full backup captures all selected data, while incremental backups only capture data that has changed since the last backup of any type. Differential backups record data that has changed since the last full backup, providing a different balance between storage consumption and speed of restoration. Understanding the difference between these types is vital when you're tasked with recovering data during an incident. Maintaining a clean and organized workspace is often overlooked, but it is essential for efficiency and safety under the 5S principles of SORT: set in order, shine, standardize, and sustain. A cluttered environment makes it difficult to track small components like screws or jumper settings, which can lead to preventable hardware damage. Sorting your workspace involves removing unnecessary cables or broken peripherals that no longer serve a function. Setting things in order means creating designated spaces for tools and spare parts so they can be retrieved instantly without search time. Consistent cleaning, or the shine step, allows you to detect physical damage or fluid leaks that might otherwise go unnoticed. When you standardize and sustain these practices, you ensure that anyone stepping into your workstation can operate at the same efficiency level as you. Professionalism in IT is fundamentally about creating a predictable, organized, and safe environment for everyone involved. See you in the next lesson. Welcome back. In this lesson, we will examine the formal practice of documentation and structured change management within a professional IT environment. Documentation is often perceived as an administrative burden, yet it serves as the foundational memory of any robust infrastructure. Without accurate records, an IT department relies entirely on tribal knowledge, which is a dangerous liability. When a senior technician leaves an organization, they take their unwritten expertise with them, leaving the remaining team to troubleshoot legacy configurations blindly. By formalizing our processes, we ensure that technical debt remains manageable and that any team member can interpret the status of our environment. Good documentation is not just about writing things down. It is about creating a source of truth that is accessible, accurate, and consistently updated during every maintenance window. If you manage an asset, you must document its life cycle from procurement to eventual decommissioning. Inventory tracking and hardware registries are the primary mechanism for financial and security oversight. Every device, from a workstation to a core switch, should be assigned a unique asset tag, which links the physical hardware to its entry in your inventory management system. This system should track manufacturer details, warranty expiration dates, and physical location. Coupling this with regular software license audits prevents legal and compliance risks, as you must be able to prove that the organization possesses valid licenses for all installed applications. When you audit your environment, you are effectively verifying the integrity of your technical assets. This data informs budget cycles and lifecycle replacement strategies, ensuring that hardware is swapped before it becomes a critical point of failure. Visual representations of infrastructure, such as network topology diagrams and rack maps, are indispensable during major outages. A network diagram provides a logical view of how data flows across your subnets, VPN tunnels, and firewalls, allowing you to trace connectivity issues systematically. Rack maps serve as the physical counterpart, detailing the specific use space each server or switch occupies within the data center. Beyond rack layout, logical port labeling and consistent cable management are vital for system maintenance. If you cannot identify which port on a patch panel corresponds to a specific wall outlet, your troubleshooting time will increase exponentially. Labeling everything according to a strict global naming convention removes ambiguity when you are performing emergency repairs in a dark, noisy server room. Knowledge base articles function as the institutional memory for recurring user issues. When you solve a complex ticket, the steps you took should be transformed into a documented procedure that allows lower-tier support staff to address the same issue independently in the future. A well-written article defines the symptom, the confirmed cause, and the step-by-step resolution, preferably verified by another technician. This lowers the volume of support tickets and facilitates faster mean time to resolution for the entire department. Furthermore, standard operating procedures, or SOPs, should be created for routine tasks like provisioning a new user or performing server backups. By codifying these steps, you minimize the risk of human error during repetitive tasks that might otherwise be performed differently by each technician. Change management is the disciplined process of ensuring that technical modifications are handled with minimal impact on service availability. In many organizations, this is governed by a Change Advisory Board, or CAB, which evaluates the risks, business impacts, and technical requirements of a requested change. A formal change request must clearly state the objective and provide a detailed implementation plan. Perhaps most importantly, every change must include a robust rollback plan, which outlines how to revert to the previous stable state if the implementation fails. Without a predefined exit strategy, you might find yourself stuck in a broken configuration during a scheduled outage. Change management forces you to think through the consequences of your actions before touching production systems. Security must be observed when managing access to documentation and administrative credentials. Storing passwords in spreadsheets or text files on shared drives is an unacceptable practice, as these files become attractive targets for attackers. Instead, utilize an enterprise-grade password manager that supports role-based access control and detailed audit logging. These tools ensure that passwords are encrypted at rest and that only authorized personnel can access the credentials they need for their specific duties. Regularly auditing these access logs helps you identify potential misuse and ensures that permissions remain current as team responsibilities shift. Treating password management as a core component of your documentation strategy protects the organization from both external intruders and internal accidents. I look forward to our next session together. Welcome to the chapter on advanced helpdesk scenarios and escalations, where we refine your ability to navigate the most challenging aspects of IT support. Over the coming lessons, you will learn how to handle multi-layered technical failures, master the art of escalation, and maintain composure while managing high-pressure environments. In this chapter, we transition from isolated troubleshooting to the management of complex, multivariable incidents. Technical problems rarely exist in a vacuum, as a malfunctioning printer often relates to a corrupted print server or an intermittent network drop might stem from a failing switch port rather than the client workstation. When you face situations where both hardware and networking layers seem compromised, the objective is to isolate variables systematically rather than throwing solutions at the wall. You must use tools like ping, traceroute, and hardware diagnostic logs to determine whether the fault resides in the physical layer, the data link layer, or a software configuration. By compartmentalizing these variables, you prevent yourself from becoming overwhelmed by the noise of cascading errors. Once you have ruled out the local components, you gain the clarity needed to proceed to more advanced internal diagnostics. This methodical process serves as the foundation for all professional-grade troubleshooting, moving you away from guesswork toward evidence-based resolution. Knowing when to escalate a ticket is perhaps the most significant milestone in a support technician's professional growth. Not every ticket belongs on your desk, and holding on to an issue beyond your scope or authority wastes valuable organizational resources. You should escalate to Level 2 or Level 3 support when you have exhausted your internal knowledge base and standard troubleshooting procedures without success. Consider the time to resolution versus the complexity of the issue. If an incident requires administrative access to core database servers or deeper network infrastructure changes beyond your current permissions, escalation is the only logical step. Always document what you have tested, including specific error codes, reboot attempts, and configuration changes you performed. This detailed handoff prevents the next engineer from asking the user to perform the same steps, which is the fastest way to lose a user's trust and damage the professional reputation of your department. Effective communication in these handoffs acts as a force multiplier for the entire IT organization. Prioritization is a constant balancing act between impact and urgency within the framework of your service level agreements. Impact refers to the measure of the effect of an incident on business processes or users, while urgency represents the speed at which the business requires a resolution. A single executive losing access to email may have high priority due to the impact on the business, whereas a printer failure in a corner office may have low urgency despite being a hardware issue. You must align your daily workload with these definitions rather than simply working through tickets in a first-in, first-out order. Managing VIP requests requires a specific form of professionalism where you acknowledge the pressure while maintaining a calm, objective demeanor. These individuals often do not understand the technical constraints, so brief, high-level summaries are far more effective than delving into the minutiae of patch management or latency issues. By treating SLAs as a contract of service, you remove emotion from the queue and bring consistency to your daily operations. Intermittent issues are arguably the most frustrating challenges you will face, as they inevitably seem to vanish the moment you begin an investigation. To diagnose these ghosts, you must shift your mindset toward continuous monitoring and log analysis rather than direct observation. Collect system logs from the event viewer, examine network utilization metrics, and look for patterns in the time of day or the specific applications running when the failure occurs. Tools like Quick Assist or TeamViewer are invaluable here, as they allow you to observe the user's environment in real time or examine a machine remotely without the potential for external bias. When an issue is hard to reproduce, look at the delta between the reported time of failure and the system state logs. Often, the answer is hidden in the background processes or scheduled tasks that align perfectly with the user's report of a crash. Patience is your greatest tool, as rushing a diagnosis based on incomplete data leads to misidentified root causes. Helpdesk technicians often act as the front line for large-scale IT projects, such as company-wide hardware refreshes or operating system migrations. During these periods, your role expands from individual incident resolution to providing standardized support as part of a larger, coordinated effort. You are essentially the point of validation for these rollouts, ensuring that the deployment scripts or hardware images function as expected across diverse user configurations. When you encounter failures during these transitions, you're not just fixing one machine, but contributing to the success of the entire infrastructure lifecycle. This requires a heightened attention to detail and clear, consistent documentation of findings. By contributing successfully to these initiatives, you prove your value as a strategic asset rather than just a reactive support agent. Engaging with these projects provides a unique vantage point on how your daily work integrates into the larger architecture of the enterprise. Staying relevant in an industry defined by rapid change requires a commitment to a cycle of learning that never truly concludes. Technology evolves, and the tools you use today will likely be obsolete within a few years, making your ability to learn new systems and protocols more important than your existing knowledge. Reflect on your recent tickets, identify areas where you felt unprepared or slow, and seek information that bridges those specific gaps. Whether it is a new version of Windows, a cloud service integration, or a shift in security protocols, your professional growth depends on this perpetual curiosity. Treat every obscure error message you resolve as a building block for your future capabilities. By consciously curating your expertise, you ensure that you remain a capable, effective member of the IT support community regardless of the technical environment. See you in the next lecture. Welcome to the concluding module where we synthesize our technical knowledge and bridge the gap between classroom theory and professional practice. We will review our core competencies and discuss how to effectively transition into an operational IT support career. To wrap up our technical foundation, consider how each layer of the OSI model correlates to the hardware and software systems we explored. When you encounter a connectivity issue, you should instinctively mentally traverse the stack from the physical cabling or wireless signal up to the application layer. Remember that high-frequency ports like 80 for HTTP, 443 for HTTPS, and 22 for SSH are not just numbers to memorize, but fundamental signals for service accessibility. Similarly, becoming proficient with command line utilities such as ping, IP protocol configuration, traceroute, and netstat provides a diagnostic edge that graphical interfaces often obscure. Mastery of these tools is a prerequisite for rapid troubleshooting, as they allow you to interface directly with the network stack without the overhead of heavy desktop environments. Relying on these primitives ensures that you understand the underlying state of the machine rather than reacting to vague error messages. As you prepare to validate this knowledge through certification exams like CompTIA, A+, or Network Plus, your strategy should shift from rote memorization to identifying the intent behind each objective. These exams function as a mirror to real-world scenarios, so approach them by asking what a technician would do when faced with a system failure or a security policy conflict. If you're preparing for the Google IT Support Professional Certificate, focus heavily on the troubleshooting methodology and the logic of service management. Technical breadth is important, but these certifying bodies prioritize the ability to diagnose issues systematically according to established industry frameworks. Use the documentation standards we discussed throughout this course to ensure your practice labs are as rigorous as the actual exam environments you will eventually navigate. Moving into the professional domain, your resume should translate academic and lab experience into tangible business outcomes. Avoid listing software names in isolation and instead describe how you use those tools to solve specific problems or streamline user access. Your LinkedIn profile serves as your digital presence, so ensure your summary reflects an analytical mindset capable of handling escalated help desk tickets. Hiring managers look for evidence of your logical problem-solving process rather than an exhaustive list of every application you have ever installed. Highlight your participation in any community forums or personal projects, even if they are modest, to demonstrate an active interest in technology. A clean, professional summary that emphasizes your ability to communicate complex issues to non-technical stakeholders is often more valuable than a list of certifications alone. The importance of soft skills in the IT support sector cannot be overstated, as you are frequently the primary point of contact for users during stressful technical failures. Your ability to de-escalate a situation while maintaining a methodical, fact-based approach is what distinguishes a competent technician from an exceptional one. Always articulate your steps clearly so that the user feels supported rather than disregarded by technical jargon. This rapport is essential for effective documentation, as users are more likely to provide accurate, honest details about incident triggers if they feel respected and heard. Keep in mind that human error remains a leading cause of technical incidents, and your soft skills are the primary mechanism for mitigating the frustration associated with those events. Lifelong learning is the only viable strategy in a field that shifts its architecture as rapidly as ours. What we have covered here is an essential primer, but the landscape will continue to evolve toward deeper cloud integration and automated management solutions. Treat this course as the starting point for a cycle of continuous improvement where you seek out new challenges and refine your existing scripts and workflows. The IT support community is vast and generally welcoming to those who demonstrate a genuine curiosity and a willingness to perform their own due diligence before asking for help. By applying the principles we discussed, you will be well equipped to navigate not only your first help desk role, but the many specialized career paths that follow. Good luck with your journey into the professional world. See you in the next phase of your development.